Good morning, my dear students. In this video session, let us learn what do you mean by a truss, what are the assumptions made in the finite element analysis of a truss, what is the relationship between local and global nodal displacements of a truss, and calculation of direction cosines, a stiffness matrix for a truss element. Now, what do you mean by a truss? What is the definition of a truss? A truss is a structural member which is a combination of two or more bars which is used to take up the load. Example, you can say bridges, towers, already you have seen. If you take an example of bridges, you have seen here the bridges are the combination of two or more bars, and these bars are interconnected by means of joints like this. Okay, and these bridges will take up the load. These are the load carrying structures. Okay, and all these bars are interconnected by means of joints, and these joints are assumed to be frictionless pin joints. Hence truss is called as pin jointed member. And due to the loads applied on the bridges, the truss structures, each bar of a truss is either induced with the tensile or compressive force, that is, each bar either expands or contracts due to the load applied on a truss member. Hence truss is also called as a two force member. Okay, now next we'll move on to what are the assumptions which are made in the finite element analysis of a truss problem. Now, first assumption is a load on a truss can only be applied at the nodes or joints. At the nodes or joints, if you consider an example of a two bar truss, here the all the bars are interconnected by means of joints. In this two bar truss, it consists of two bars, hence it is named two bar truss. And these two bars are interconnected by means of joints like this, and all the joints are represented by nodes in FEM. Okay, and first assumption says a load on a truss can only be applied at the nodes or joints. That means a load can only be applied at the nodes or joints like this. It should not be applied at the midway of the bars like this. It is wrong. Okay, now first assumption is what? To carry out the analysis on a truss member, a load can only be applied at the joints or nodes. Okay, now come to the second assumption, that is, due to this load applied, each bar of a truss is either induced with tensile or compressive forces. That means if you take the same example of a two bar truss, it is a combination of two bars that is having three joints, that is three nodes. Due to this particular load applied, let us say it is having a deformed shape. I will draw here dotted line. In dotted line I will show the two number joint 2 will attain the new position 2 dash after deformation. Okay, then you can observe here this element, this bar has been expanded like this due to the load applied, and this bar has been contracted like this. Contracted, it is going to be contracted. Hence due to the load applied, second assumption says due to the load applied, each bar of a truss is either induced with tensile or compressive forces. Now, third assumption, the joints in a truss are assumed to be frictionless pin joints. As we know that in a truss member, which is a combination of bars, and all the bars are interconnected by means of joints, and these joints are assumed to be a frictionless pin joints. These joints are assumed to be frictionless pin joints. Hence all the bars are free to move about their pinned ends. Hence truss member is also called pin jointed member or pin jointed configuration. Truss is also called pin jointed member or pin jointed configuration, because all the bars are assumed to be interconnected by frictionless pin joints. Now next come to the fourth assumption, the self weight of the bars of a truss are neglected in comparison to the external load applied. That means the self weight of the truss we are not considering, we are neglecting the self weight of the truss structure. We are considering only the external load applied while carrying out the analysis. These are the four assumptions, okay, which have to be made in the analysis of a truss. First assumption, a load on a truss can only be applied at the nodes or joints. Second assumption, due to the load applied, each bar of a truss is either induced with tensile or compressive force. Hence it is also termed truss is also called two force member. And third, the joints in a truss are assumed to be frictionless pin joints. Hence, the truss member is also called pin jointed member or pin jointed configuration. And fourth assumption, the self weight of the bars of a truss are neglected in comparison to the external load applied. Okay, now next we will move on to we will discuss the relationship between local and global nodal displacements. Okay, what do you mean by local and global? The local refers to the single element and global refers to the entire structure, as we know. Okay, now come to, if you consider a single element of a truss, this figure shows having two nodes 1 and 2, and the local coordinate is the one which passes through these nodes 1 and 2, that is x dash. X dash is the local coordinate, and the global coordinates are x and y. Okay, x dash is the local coordinate and the global coordinates are x and y. Okay, that for example, if you take that we took example of 2 bar truss, due to this load applied p, let us have it is going to deform like this. The node 2 will attain the new position like this. Here you can observe this along the element, the deformation will be like this. This is what u1 dash. Okay, and in x direction, this is the local displacement. Global displacement, if you say this node 2 will have in x direction, it is u1, and in y direction it is having like this, in y direction, that is u2. Like this, the local and global displacements have to be related, that we will discuss later. This is local coordinate is the x dash which passes through the nodes 1 and 2, and the global coordinates are x and y. Okay, now we will deduce the relationship between local displacements and the global displacements. Okay, now let us consider this truss element 1 to having two nodes 1 to 2. Due to the load applied, let us assume that this truss element will attain the new position like this. Okay, will attain the new position like this. This truss element will attain the new position like this due to the load applied. Okay, now what are the local displacements? We'll find out now. Local displacements is along the element, that is this node number 1 will attain the new position here due to the load applied, and node number 2 will attain the new position here, okay, due to the load applied. Okay, now next now node number 1 will attain new position here, node number 1. Then what is the local displacement? Local coordinate is going to be represented by x dash and displacement is represented by u. That's why I took the notation as at node 1 the local displacement is, I have shown here, it is along the element. This is what u1 dash I have shown. u1 dash is the local nodal displacement which is along the element. Along the element only it is to be measured. This is the local nodal displacement at node 1, that is u1 dash. Okay, likewise u2 dash is the local nodal displacement at node 2, local displacement. Okay, now come to global displacement. Globally, if you consider the entire structure, then the node number 1 will attain the new position 1 here. That means global coordinates x and y. In x direction, what is the displacement it is having? That is 1 to 1, that is in x direction we should measure, that is u1. u1 is the global nodal displacement in x direction at node 1. And next what one more global displacement we have, that is u2, that is in y direction. We should measure how much the node number 1 is displaced to this location. In y direction, if you measure like this, in y direction it is, if you measure, that is u2, that is u1 is the x component of displacement at node 1 and u2 is y component of displacement at node 1. These are the global displacements. Likewise for node 2, Okay, for node 2, u3 is the x component of displacement at node 2, u4 is the y component of displacement at node 2. Hence you can conclude that globally each node of a truss element having 2 DOFs, 2 degrees of freedom. Each node is having 2 degrees of freedom, that is 2 unknowns. Okay, and locally in local coordinates each node is having only 1 degree of freedom, that is one unknown u1 dash and u2 dash at each node. Okay, now now we'll move on to, here I wrote u1 dash u2 dash be the local nodal displacements, u1 u2 u3 u4 be the global nodal displacements. Okay, now we will deduce the relationship between local and global nodal displacements, because local displacement already we know. If we deduce the relation between local and global nodal displacement, that will help us to derive the stiffness matrix for a truss element. Okay, just what is this local? This local coordinate is going to be transformed into global coordinates like this, just by using the value theta, because all the bars of a truss structure are inclined in nature. Okay, I hope you are following. Hence now if you consider this, here node, now just I did some modifications in the geometry in this figure. You can observe here, what is this? Now this is what the u1, I have shown the dotted line here, and this is what the u2, I have shown the dotted line here. From this next this is what u1 dash. Okay, I wrote next, after that I did some modification like this. Okay, now this is what the right angled triangle we got. How we got this right angled triangle? Just I have from this point, just I have extended this. Okay, I just wrote this as named A and this as B. Okay, and next u1 dash will become A plus B. Okay, now we will find what is A and B. How we will find A and B? That is, I will consider first this right angled triangle. If I consider this right angle triangle, let us say this is the angle of inclination of this bar with the horizontal with the ground, that is theta. Okay, now if you consider this right angled triangle, then cos theta is equal to A. What is cos theta? Cos theta is adjacent is A, divided by hypotenuse is u1, that is hypotenuse is this one, that is u1. u1 is the hypotenuse, therefore A will become u1 cos theta. Okay, now next come to second right angle triangle, this one. Okay, in this right angle triangle, okay, if this is theta, then this one will be 90 minus theta, correct? Okay, if this is theta, then this angle will be 90 minus theta. If this is 90 minus theta, then this angle will become, what is that? That is this angle. Okay, now this angle, okay, this angle will become 90 minus theta. This angle 90 minus theta. If this is theta, then 90 minus theta, and if this is 90 minus theta, this angle will be theta. Okay, now from this right angled triangle, if you write sine theta, then sine theta is equal to, opposite is this one, that is opposite, this is given, that is B. That is B. Sine theta is equal to opposite divided by hypotenuse, that is hypotenuse will be this one, that is this is u2. Okay, sine theta is equal to B by u2, hence u2 is equal to B sine theta. Here you can observe, I wrote here B is equal to u2 sine theta by considering this right angle triangle. That is sine theta is equal to opposite side is B and hypotenuse is u2, that is B by u2 sine theta, and B is equal to u2 sine theta. Therefore now we got the relationship between local and global nodal displacement. What is that? A plus B, if you add these two equations, we will get u1 cos theta plus u2 sine theta. Therefore what is A plus B? That A plus B is u1 dash, that is local displacement. u1 dash is equal to u1 cos theta plus u2 sine theta. Similarly we will get for node 2 also, if you do the same this one from the geometry, if you go through the trigonometric functions, you will get similarly u2 dash. This u2 dash is equal to u3 cos theta plus u4 sin theta. Okay, I hope you have understood. Now now we will move on to the next page. Okay, here now the direction cosines. I hope you have understood this one, the previous page. What is that? Okay, now we got u1 dash is equal to u1 cos theta plus u2 sin theta, u2 dash is equal to u3 cos theta plus u4 sin theta. u1 dash and u2 dash are the local displacements. u1, u2, u3, u4 are the global displacements. And this I have shown, this is a numbering scheme for a 2D problems. This is a 2D truss because at each node there are two unknowns. One is x component of displacement, another one y component of displacement. Hence how do we go for the numbering? I indicates that is the node number. If node number is 1, what is the scheme? u2i minus 1 and y component will be u2i. If you put I is equal to 1 here, you will get u2i minus 1, that is 2i minus 1 will be 2 into 1 minus 1, that is 1 u1, and 2i means 2 into 1 2, that is u1 u2. If the node number is 2, if I is 2, then 2i minus 1 will be 2 into 2 minus 1, that is you will get u3, and u2i, that is 2 into 2, that is you will get 4, that is 3 4. For node number 3, 5 6, like this and so on. The DOF numbers you will get for node number 1 u1 u2, for node number 2 u3 u4, for node number 3 u5 u6, because there are two unknowns at each node, that is one is x component of displacement, another one y component of displacement. Like this you should know how to write the DOF numbers for the. Okay, now u1 dash is equal to, we got the relation local displacement. This is going to be you can say resolved by an angle theta. It is going to be resolved into two, that is one is u1 and another one u2. Likewise this u2 dash, it is going to be resolved one in u3 and another one in u4. Likewise for the relationship we got, u1 dash is equal to u1 cos theta plus u2 sin theta, u2 dash is equal to u3 cos theta plus u4 sin theta. Okay, now the first equation is for node 1. This equation is for node 1. u1 dash is the local displacement at node 1. u1 and u2 are the x and y component of displacement at node 1. And second equation represents that is for node 2. u2 dash is the local displacement at node 2, and u3 and u4 are the x and y component of displacements at the node 2. Okay, now next we will move on to the direction cosines. Okay, direction cosines are represented by L and M. Okay, for this, what are direction cosines? Direction cosines are the cosine of the angle between local coordinates and the corresponding global coordinates. Okay, now I will consider the element truss element having nodes 1 to 2, and it is inclined with the horizontal. Let us say it is inclined with the horizontal, that is theta. If this is theta, then it will be 90 minus theta, and the coordinates, global coordinates are x and y, and the local coordinate is x dash. Okay, what are direction cosines? Direction cosines are the cosine of the angle between local coordinates and the global coordinates. Now first, what is L now? Direction cosine. First direction cosine I will find. L is equal to cosine of x and x dash, that is global coordinate and the local coordinate angle. Cosine of the angle between this x and x dash, that is cos of x dash, that is equal to, what is the angle? You have considered cos theta. Okay, what is M now? M is equal to cosine of the angle between this local coordinate x dash and y, that is cos of x dash y. Cos of x dash y is 90 minus theta, that is cos of 90 minus theta will give you sin theta, that is M is equal to sin theta. One direction cosine L is cos theta and another direction cosine M is sin theta. Just what we will do in the relationship between the local and global displacements equations, we will just replace cos theta and sin theta by L and M. L and M. Just we will replace this cos theta and sin theta by L and M. Okay, now that is what, if you replace, then we will get in terms of L and M, the direction cosines, that is u1 dash will become u1 into cos theta, that is I will write u1 into L, plus u2 into sin theta, I will write u2 into M. Likewise, u2 dash is equal to u3L plus u4 M. In terms of matrix form, if you write u1 dash u2 dash is equal to LM0000 LM is into u1 u2 u3 u4, that means in terms of matrix form, if you write, you will get these matrices. That means this will give you these two equations. The two equations you have, u1 dash is equal to L into u1 plus M into u2, the remaining are 0, that is u1 into L plus u2 into M, and u2 dash is equal to these two are zeros, hence u3 into L and u4 into M. The same equations we will get in matrix form, we will get like this. Therefore, in shortcut you can write u dash is equal to L into u. What is u dash? U dash is the local nodal displacements. L is nothing but the transformation matrix. That means this transformation matrix is the matrix which is used to transform the local displacements to the global displacements by using the direction cosines L and M. Okay. Now next, now U is the global nodal displacements. That is, in short, you can say this relation you should remember, dear students. U dash is equal to L into U, where U dash is the local nodal displacements and U is the global nodal displacements, and L is the transformation matrix which is used to transform the local to global nodal displacements. And this relation is going to be helpful in further derivations on stiffness matrices and stress matrices for the truss element. Okay, I hope you have understood. Now we'll move on to next, the calculation of direction cosines in a truss element. How do we calculate the direction cosines in a truss element? Okay, first, to calculate the direction cosines are L and M. Okay, because cos theta and sin theta are the L and M. If theta is not given, because theta is not going to be given, just you need to find L and M by using the coordinate values of the nodes of a truss element only. That's why we should know how to calculate the direction of this one, direction cosines in a truss element. For that, I will consider this truss element having true nodes 1 to 2, which is inclined at an angle theta with the ground. Okay, now next, here let us say the coordinate values of the node 1 is x1 y1 and coordinate values of the node 2 is x2 y2. What do you mean by this x1 y1? From the origin, this node 1 is at a distance x1 in x direction. From the origin, this node 1 is at a distance y1 in y direction, and node 2 from the origin it is at a distance x2 in x direction, and from the origin node 2 is at a distance y2 in y direction. Okay, now if let us say origin is here and this is x1 and this is y1, like that. Okay, if you note 2 from the origin it is x2, okay, and then from the origin it is y2, like this. Okay, next, if you, now I will form a right angled triangle like this by using these dotted lines. I will just join, okay, so that I will get this right angled triangle. In this right angled triangle, this side already we know that is what the length of the element, that is the length of the element. This is the length of the element. Okay, now what is this side and this side in this right angle triangle? From the coordinate values we will come to know this side will become, if this is x2 value, because this is in x direction, this side is in x direction, if this is x2 value and this is x1 value, then this side will become x2 minus x1. Okay, and this is the side in y direction, hence now this side value will be, this is in y direction, it is coordinate value is y2, in y direction it is y1. That is, you can say if origin is here, this is y1, and from the origin it is y2. If I want to know only this much distance, then you should go for this y2 minus y1. If you do, you will get this distance. Hence the side, this side will be y2 minus y1, so that we got this right angled triangle. Okay, now from this right angle triangle we will deduce the equations for LE, length of the element, and direction cosines L and M. Okay, from the right angled triangle what is cos theta? Now we'll find cos theta. We know one of the direction cosine, that is L. What is cos theta? This cos theta is equal to adjacent by hypotenuse. Okay, what is adjacent? Cos theta is equal to adjacent is x2 minus x1. Okay, I wrote x2 minus x1 divided by hypotenuse is this one, LE, that is opposite to the this angle. Okay, 90 degrees angle, that is what, x2 minus x1 by LE. And what is sine theta? Sine theta is equal to opposite is y2 minus y1 divided by hypotenuse is LE, hypotenuse is LE. Okay, then what is sine theta? That is, it is represented by m. Hence we got the formula to find the direction cosines L and m, that is L is equal to x2 minus x1 by LE and m is equal to y2 minus y1 by LE, where x1, x2, y1, y2 are the coordinate values for the nodes 1 and 2 and LE is the length of the element. How do we calculate the LE value, length of the element of a truss? From the Pythagoras theorem, the square of the hypotenuse square is equal to the summation of the squares of the both sides. From that, this LE square is equal to x2 minus x1 whole square plus y2 minus y1 whole square. Then what is LE? LE is equal to square root of this x2 minus x1 whole square, y2 minus y1 whole square. This is the length of the each element of a truss structure can be calculated. Length of each element of a truss structure can be calculated by using this formula. But coordinate values should be known. Coordinate values of all the nodes of a truss should be known to us. If the coordinate values are known, we can find out the L and M direction cosines, okay, and also length of the element of a truss structure. And the stiffness matrix for a truss element is given by, to generate the stiffness matrices for all the elements of a truss structure, we should use the formula to find the stiffness matrix for element, that is given by AE by L. AE is nothing but A suffix E, area of the element. This small e represents element number. E, Young's modulus of the element. LE is the length of the element. AE by L outside, and inside you should write L square LM m square, and this is the formula. And you can observe here order of the matrix, we have here 4 cross 4 for 1D bar problem. This one for different problems on bars, we have used the stiffness matrix formula AE by L 1 minus 1 minus 1 1. Order of the matrix we have used 2 cross 2 only, but here it is 4 cross 4 for order of the matrix for a single element of a truss, because here for a single element of a truss, at each node we have two unknowns, that is at each node, at node 1 x component of displacement, y component of displacement, at node 2 x component of displacement, y component of displacement. Totally for a single element of a truss structure having two nodes, how many unknowns we have totally? At node 1 two unknowns x and y, and at node 2 we have two unknowns x and y. Hence total number of unknowns for a single element we have 4 unknowns. For a single element of a truss we have 4 unknowns, that is 4 DOFs. Hence order of the matrix will be 4 cross 4. This is one of the property of the stiffness matrix. But in case of problems on different cross section bars, each node is permitted to displace only in x direction. Hence at each node only one unknown, then two nodes, two unknowns. Hence order of the matrix we got stiffness matrix 2 cross 2 we are using. But here in the formula for stiffness matrix of a truss element, the order of the matrix we should use 4 cross 4 we got after derivation, because at each node there are two unknowns, totally two nodes, we will get 4 unknowns. Okay, hence we got this for order of the matrix 4 cross 4. This is the difference between bar element and truss element. Bar element, there are for a element having two nodes, at each node only one DOF, 1 degree of freedom, one unknown. Hence there are two unknowns. Hence order of the matrix will be 2 cross 2. But in a truss element, at each node there are 2 degrees of freedom, two unknowns x and y component of displacement. Hence for a single element of a truss having two nodes, there are 4 DOFs, 4 unknowns. Hence order of the matrix will be 4 cross 4. Okay, how to remember this matrix formula? AE by L common outside, you should know. First you remember this term L square LM m square. These are the direction cosines. What is L and M are the direction cosines. Okay, L square LM m square, and as we know that stiffness matrix is a symmetric one, the same L square Lm Lm m square you should write here symmetric to this, and the same L square Lm Lm m square negative of these values write it here, and symmetric of this minus L square minus Lm minus Lm minus m square. Like this you remember this formula, okay, for the stiffness matrix of a truss element. Okay, how to calculate area and Young's modulus will be given in the problem, and length of the element, how do you calculate? If it is directly given horizontal or vertical values are given directly, you take the length of the element. If it is inclined one, then you should calculate. How to calculate the length of the truss element? By using this formula already we have discussed here, x2 minus x1 whole square plus y2 minus y1 whole square, where x1 y1 is the initial node coordinate value, x2 y2 is the final node coordinate value. In the next video session, for the problem on a 2-bar truss, you will come to know how to solve the problems on a truss by considering the nodal data, coordinate values, and length of the element and direction cosines. And L and M are the direction cosines. How do you calculate the direction cosine? L is equal to x2 minus x1 by LE. Okay, LE already you know, just you have to substitute here. And what is x2 and x1? These are the coordinate values that you should know. You should find out the coordinate values given in the figure of the problem. You just substitute and get the values of L and M by using these two formulae. Okay, once you find the L, M and LE, then you just substitute here and get the stiffness matrix for all the elements of a truss and assemble those matrices to get the global matrix and global equilibrium equation. Apply elimination approach to determine the unknown nodal displacements and stresses each element and support reactions, as I am going to discuss in the next video of this truss problems. I hope, dear students, you have understood this session. In this session, what we have covered in this session, that is what do you mean by a truss, definition of a truss. Okay, we have discussed definition of a truss, assumptions made in the FEA of a finite element analysis of a truss, 4 assumptions. Next, we have discussed what are the local and global coordinates. Local and global coordinates we have discussed. Okay, local coordinates and the global coordinate, local x dash and global coordinates x and y, and the relationship between the local and global nodal displacements. And next, we have discussed the direction cosines. Direction cosines we have discussed, that is a cos theta is L, M is sin theta. Just we have replaced and we got the relationship between local and global node displacements in this matrix form. And next, we have discussed calculation of direction cosines. How do we calculate the direction cosines L and M from the right angled triangle which is going to be formed? And stiffness matrix for a truss element is given by this one. Order of the matrix will be 4 cross 4 because each element of a truss having 2 degrees of freedom at each node, 2 unknowns at each node. Hence, for a single element having 2 nodes, totally there are 4 degrees of freedom, 4 unknowns. Hence, order of the matrix of a single element of a truss will be 4 cross 4. That is one of the property of the stiffness matrix. Already we have discussed. Okay, all these things we have discussed. In the next video, I will explain you how to solve the problem on trusses. Okay. I hope you have understood, my dear students. This is the basic. This is the basic of a truss. This video session is very important. You should know all these things. What is covered in the truss. If you understand this better, then you can solve any of the problems by going through the procedure, which is going to be explained in the next video. Okay, and also you can observe here what difference you have observed between the bars and truss. What is the difference in case of bar? If you consider a bar problem, here each node is permitted to displace only in x direction, globally and locally. If you consider if there are two elements, okay, and locally in local coordinates, that is each element, if you consider, then each element is going to displace only in x direction only. If you consider globally also, globally entire structure also, each node is permitted to displace only in x direction. That is local coordinate is also x and global coordinate is also x. That is local and global coordinates are same in case of bar. In case of truss, local coordinates, if you consider a single element, then local coordinate will be along this, which will pass through these nodes, that is x dash is the local coordinate, but global coordinates are x and y. X and y are the global coordinates. Okay, local and global coordinates are different for this one truss element. But since the each bar of a truss element due to the load applied is either induced with expansion or contraction, hence that is the local coordinate is x dash, and in local, hence in local coordinates bar and truss element are same. In local coordinates bar and truss elements are same, but in global coordinates these two are different. Okay, and one more difference, if you go for a single element of a bar, for a single element of a bar having two nodes, each node is permitted to displace only in x direction, hence degrees of freedom will be at each node 1, then total 2 degrees of freedom, then order of the matrix you will get stiffness matrix 2 cross 2, that is 1 minus 1 minus 1 1 the formula. And in case of truss element, if you consider having two nodes only, at each node there are two unknowns, at each node 2 degrees of freedom at each node, hence the order of the matrix will be 4 cross 4, hence the stiffness matrix order you will get here, as in this case 4 cross 4. Okay, thank you dear students. Any doubts you just let me know, and I will clarify your doubts. Next video session you just go through the procedure of solving the problem on a 2 bar truss. Thank you. Thank you. Take care. Stay safe. Stay healthy.